Hello, Math 120, and this is Professor Gonzalez, and I'd like to do some problems from homework section 7.6. Now, 7.6 is entitled, what is it called? Polynomial inequalities. So you can see we have a polynomial on the left, and an inequality, and this particular one is set greater than or equal to 0. So a couple different ways. You could do this graphically, but one way that's the book uses, and pretty, I think, one of the more common ways of doing this, is to find critical values. So what you do is you temporarily look at this as an equation. So we say x minus 4, quantity x minus 4 times the quantity x plus 5. Now you might have the knee-jerk reaction to multiply that out, but it's equal to 0. So then all we have to do is set each factor equal to 0. And we've done this a lot. We know this is going to give us x equals 4. And set the second factor equal to 0, and we get x equals negative 5. So these are going to be critical values or critical points. Values is good enough. And then what we do, and we've done this before with rational inequalities. It's a similar thing where we go ahead and make a number line. We write down our critical values. And those critical values happen to be, and let's put 0 here, negative 5 over here, positive 4 right about there. And then we divide this into regions, right? And then we test those regions, right? So we've got, we've got this region, we've got this middle region, we've got this region to the right. So we need to test. So we go ahead and get a test point that's in this region, like x equals negative 6. Now when we test, we go back to our original problem that we used to test with. Now this original problem is all factored, which is really easy to test with, meaning we could replace our x values with negative 6 and actually get the exact number, negative 6 minus 4 times the quantity negative 6 plus 5, and answer the question, is that greater than or equal to 0? But since you're comparing it to 0, you really only need to look at the sign. So I wouldn't go through as much trouble. I would just say, okay, a negative 6 minus 4, well, that's negative. And a negative 6 plus 5, that's negative. And so when you have them written as factors and comparing it to 0, this works really quick. Negative times negative is a positive. Is a positive greater than or equal to 0? And that would be true. So that means we're going to shade. We're going to shade this region. Everything in this region is going to make that inequality true. So then we go ahead and look at this region in the middle, and 0 looks like the easiest number to try. I'm going to use the idea of just using positive negative symbols. So if I put in a 0 in for x here, I get a negative number. Put in a 0 for x here, and I get a positive number. And that's supposed to be greater than or equal to 0. Well, a negative times a positive is a negative. Is a negative number greater than or equal to 0? And we know that that is false. So then we take a look at our final region here. X equals 5, right? Something to the right of 4. Once again, plugging that back into our original inequality. And if you put in a 5, put in a 5 in for x, 5 minus 4, well, that's going to be positive. And if you put in a 5 plus 5, that's going to be positive. Compare that to 0. Positive times a positive is a positive greater than or equal to 0, and that's true. So that region needs to be shaded also, indicating that all values in this region will make that inequality true. Now we look at the inequality, and it has an equal signs with it, so that means that we have to include our endpoints of negative 5 and 4. So how do we actually write this in interval notation? That would just be, this goes out to from negative infinity up to negative 5, and that's closed. Union, let me try that again, union, and then it's closed at 4 and goes up to positive infinity. Okay, and that's going to be the answer right here. I guess I'll write it again. Actually, why should I write it again? I don't need to do that again, but I'll just just do a little circle. And that just belongs right here. And then what graph goes with that? Let's see, that is going to be graph letter D. Matches the graph I just did up there. Okay, so that we do the problem again. The difference on this particular problem is it is not factored. So let's go ahead and find our critical values over here. So finding our critical values, we're going to temporarily set this equal. And we can see what multiplies what to negative 10 and we'll add to negative 3. Well, that's going to be a negative 5 times 2. So this factors down to x minus 5 times x plus 2 equals 0. Now we have two factors equal to 0, so we set each factor equal to 0. We get x equals 5. Set the next factor equals 0, we get x equals negative 2. These are our critical points that we're going to plot on our graph. So there's 0, there's a negative 2 there, there's a positive 5 there. There are our regions that we must test. Now remember, we're going to test with the original problem over here, and we might as well write it as factored. It'll make the testing much easier. X minus 5 times x plus 2 is greater than 0. Okay, so let's go ahead and pick a value in this region, like how about x equals negative 3. We replace the x with negative 3, and we get, on the first factor, we get negative. Replacing the x with negative 3 right there, we get a negative. And we know a negative times a negative is positive. So this is true. So we must shade. Numbers in this region are part of our solution. Looking at the next region, x equals 0 is the easiest to use. And when we plug it in, we get a negative and we get a positive. Remember, we just plugged in 0 for x right there and right there. Is that greater than 0? Well, negative times positive is negative, and negative is greater than 0. That's false. Let's try our final region, like how about 6? Plugging 6 back into these problems again, we get 6 minus 5. Well, that's positive. 6 plus 2, that's positive. A positive times a positive is positive. Is a positive greater than 0? That's true, so we shade this region. Now we can see that this is not equal to, so this is going to be open. And our solution, or written as an interval notation, would just go from negative infinity up to negative 2, union, open at 5, up to positive infinity. Negative infinity to negative 2, union 5, comma, infinity. So this is my solution written as an interval, in interval notation, which just goes right down here. And looking at my graph, which graph would match with that? Well, that would be graph letter B. I wanted to show one more way of thinking about this, an alternative way, but I think it's kind of helps a little insightfulness here. Another way to think about this is actually to look at, let's use some red, to look at this part of the inequality as an equation. Y equals x squared minus 3x minus 10. And that must be greater than this part, which we'll just say is y equals 0. So I wrote it as equations with x's and y's, which just allows us to write it in 2 dimensions. Okay. So really, you could actually graph this in 2 dimensions where you have x's and y's. So if you're going to graph the polynomial on the left, well, we already know it's x-intercepts because we did that work over here on the right. We found x-intercepts at 5 and negative 2. So let's say at 5 and at negative 2. So this graph opens up. You can see it opens up because the a value is positive. And so let's go ahead and just make that graph. You also can see it crosses the y-axis at -10. But this just has to be a rough sketch, really. It doesn't have to be perfect. Definitely has to be opening the right direction, though. So it looks something like this. Okay, and now what? We have the green, y equals 0, that's a horizontal line at 0. So in a way, what this is saying is what x values make the red taller. Why is it taller? Because look at, we've got these y values. Y equals x squared minus 3x minus 10. Well, that expression gives us our y value. So what x values makes the y value, I say taller because we're talking about the y values, taller than what? The green. And so when we take a look at this, we're talking about the height because we're talking about y values, and we want to know what x values will make that happen. Well, you can see that when we're down here, the red is smaller or less than the green. But once we get here, the x value is definitely taller or greater than the green. So therefore, these x values makes the y value greater than the green. Now at -2, it equals it. And notice we've got this inequality, not equal, so this is open. And when you look at this, in this interval, in this region right here, the red is less than the green. It's lower, shorter than the green, less than. Then it's equal. Now the x is greater than the green. So this region also works. These x values are going to make the parabola red greater than the green. And you can see that's the same exact, so the stuff in blue here is the same exact, well, let me make it blue over here, right? So the nice advantage when you actually graph it is you can kind of quickly see what's going on. And the advantage of this test points and critical values is that you don't have to graph it, right? You're just going to find the solutions that work on the number line. Okay, let's look at the next one. The next one is number 3. Now, number 3, once again, we're going to use our critical points. Finding our critical values, we write this as x squared minus 6x plus 4 equals 0. And you can see what multiplies to 4 and adds to 6 or -6 and nothing does. So we either complete the square or we use the quadratic formula. And most people are probably just going to use the quadratic formula at this point. So we use it. It's going to be x equals the opposite of b plus or minus the square root of b squared minus 4 times a1 times c4 all over 2 times a, 2 times 1. Now I always like to take this interior, which is called the discriminant, right, and just simplify that first. -6 squared is 36. Minus 4 times 1 times 4 is minus 16. So 36 minus 16 gives us what, 20? So that value is 20. Well, it's going to be square rooted, so let's go ahead and simplify that. And I can think of that as the square root of 4 times the square root of 5, so that's 2 root 5. So what do we have here? We've got opposite of -6, so we've got 6 plus or minus 2 root 5 over 2 times 1 is 2. Now you know we can factor out a 2 up top, which leaves us with 3 plus or minus root 5 over 2. So we can see a common 2 reduces, leaving us with 3 plus or minus square root of 5. Now, if you use the positive symbol, we want to look at the approximation just so we can kind of get an idea where it belongs on the graph. Usually 3 plus root 5 is not as easy to think about. It's approximately 5.24, putting it in the calculator. And 3 minus root 5, well, that's approximately 0.76. Make sure everybody knows that that was a 5. Okay, so now we want to do our critical values, and that looks something like this. There's 0. So right here, we're going to call this 0.76. What's its exact name? Exact name is 3 minus root 5. And we also had this other value, which was approximately 5.24. What's its exact name? Well, its exact name is 3 plus root 5. All right, now what? Well, now we have our regions to test. And I would not, use square roots or square root of 5 in my test. I would find some nice values. Let's see what we have. Now this cannot be factored, so we have to use that. So it's not going to be, you're not going to have that nice streamlining effect, but we can still do this. X equals 0, and then we just plug in 0 into our original for x. So what do we get when we do that? It's going to be 0 squared minus 6 times 0 plus 4 is less than 0. Well, that gives us 4 is less than or equal to 0, and that's false. So then we move on. If this is 0.76, well then x equals 1 would be an easy value to use in this region. So we do the same thing. We plug in 1 into this formula, the original. I'm talking about this original right here. This gives us 1 squared minus 6 times 1 plus 4 is less than or equal to 0. 1 squared is 1. Negative 6 times 1 is minus 6 plus 4 is less than or equal to 0. Well, this gives us a negative 1 is less than or equal to 0. That's true. So we are going to shade this region. Now, because these are parabolas, you do know that it's not going to bend back around and start working again. But with polynomials, it could have. Polynomials. These are polynomials. With rational expressions, it could have. But we still like to go through the motions. But if you do a bunch of these, you know that this, if it's a parabola, it's not going to. It's impossible that this also works. But anyhow, let's go ahead and do this. Let's use 6 as a good point since this is 5.2. And we just plug it into that original formula and see what happens. So, whoops, we're using 6. Original formula said x squared minus 6 times x plus 4 is less than or equal to 0. This gives us 36 minus 36 plus 4 is less than or equal to 0. That gives us 4 is less than or equal to 0, which is false, just like we said. And we look at the inequality, which has an equal sign in it. So we know that this has to include the endpoints. So our answer would just be, well, I'll write it up here. Our answer would just be, it goes from 3 minus root 5 up to 3 plus root 5, and it's closed. And that goes down here. And what does that match with? Looks like C. Number 4. Well, we'd like to set this equal to 0. So I'm going to go ahead and subtract 3x on the left, subtract 3x on the right, subtract 4 on the left, subtract 4 on the right. I end up with a 0 is greater than or equal to x squared minus 3x minus 4. And we like that 0 on the right usually, so let's just write it that way. It's not that critical, but let's write it that way. X squared, more of a standard form. x squared minus 3x minus 4, put a 0. Now remember that this inequality was opening up towards the 0, so you have to continue to do that. And now the question is, will that factor to find our critical points? And let's see that we've got x squared minus 3x minus 4 equals 0. What multiplies to negative 4 and adds to negative 3? And I think x minus 4 times x plus 1 will do all of that. We set the factor equal to 0, x equals 4. Set the next factor equal to 0, x equals negative 1. Those are our critical points. 0, we've got 4 out here, we've got a negative 1 right here. Let's take a look what our critical values would be. Well, we've got the critical values. Let's find some test points. Now we also know that this did factor down to x minus 4 times the quantity x plus 1 is less than or equal to 0. Got negative 1, well, to the left of that would be x equals negative 2, so let's try that. And if I put a negative 2 in here, I get a negative. If I put a negative 2 in here, I get a negative. And a negative times a negative is a positive, and is a positive less than or equal to 0? That's false. So then I try x equals 0. I put in 0 here, I get a negative. Put in a 0 here, I get a positive. Negative times a positive is a negative less than or equal to 0? That is true. So then we go ahead and shade all values in this region will make the inequality true. Then we try x equals 5 clearly in the right region. We plug it in. 5 minus 4 is positive. 5 plus 1 is positive. Positive times positive is a positive. Is a positive less than or equal to 0? That's false, so we don't shade it. We go back and take a look at the inequality. The inequality had an equal sign in it, so that means we're going to have to include that endpoint. And so this answer is negative 1 to 4, and it's closed, including the endpoint. And that just goes right there. Look at our graph, and we go see if we can find the proper graph that works, and it is A. Last problem. So we look at this last problem, and what multiplies to 6? I'm sorry, there's a z's, aren't they? What multiplies to 6 and adds to 2? And that's not possible, so we go ahead and use the quadratic formula again. Of course, we know that A is 1, we know that B is 2, and we know C equals, out of space there, aren't I? C equals 6. So the quadratic formula is the opposite of B, so opposite of 2, plus or minus square root of 2 squared minus 4 times A, which is 1, times C, which is 6, all over 2 times A, 2 times 1. As usual, I like to take a look at this discriminant and simplify it first. 2 squared is 4. Negative 4 times 1 times 6 is minus 24. We're left with a negative 20. This is going to give us an imaginary solution, right? Because we've got a negative under the radical. Now, we're graphing on the real number line system. So that means, essentially what this means is this particular polynomial, in this case it's a parabola, does not cross the x-axis. So there's a couple possibilities. So let me go back to that example that I was showing before. Basically what we're saying is, let's make this green, right? So this would be y equals 0, so you got this horizontal line at 0, and you've got this parabola. Now that parabola does not cross the x-axis, it does not cross the green. We want to know, when is the red greater than the green? So if it doesn't cross, there's a couple possibilities. It is either up here, In that case, all values of x will make the red greater than the green. Or, wonder if it'll actually grab that. Or, nope, it grabbed too much. Darn it, thought it was going to be tricky. Or, it would be down here, and then no values of x would make the parabola greater than green. My kid is calling me in the background, probably asking stat questions. But once she finds out that I am lecturing, she will leave me alone for a little longer. So now, let me see here. See if I can draw this in a little bit of a different way so I can move that around. Okay, so like I said, let me just try that again because I did get a little distracted. In this situation, they're asking when is the red greater than the green? All values, all real numbers will make the red greater than green. But in the case that the parabola happened to be below, why won't it let me do that? What if it was below? Well, if it was below, then no values of x will make the red taller or greater than the green. So it'd be no solution. So we got to figure out where this thing is. Okay, so either we graph it like that. So I'm going to put a question mark here. Question mark. Or we can just use our critical value method that we've been doing. And let me just show you how that works. So we don't have any x-intercepts. So you have one big fat region here. And essentially what you do is you just pick something on this one region, like how about that easy number in front of us, x equals 0. And we try to see, because in this situation, when you don't have x-intercepts, either everything works or nothing works. So just grab one easy value and see if it works, then all reals work, all values work. If it doesn't work, then there's no solution, no values work. So what you can do is you can grab this problem, this original problem, which said z squared plus 2 times z plus 6 is greater than 0. So then you plug in 0 for the z values. And I guess I need to clarify, we said z, didn't we? And then we simplify and we get, right, 0 here and 0 here. So we get 6 is greater than 0. Is that true or false? 6 is greater than, that's true. So that is telling us that all values work. And if all values work, as an inequality, we say it goes from negative infinity to positive infinity. And we're done. And what graph looks like that? Well, C looks like that, all values. And that is it. I hope that helped. And keep on cruising, keep on rolling, finish strong. Have a good day. Talk to you soon. Bye.